Hello, welcome to this video. I'm currently, as you can probably tell by my background, away to see a friend, and on the train up here. I was thinking over, a thing in physics that has, um, been moulding over within my mind, although now I come to think of it, moulding might not be the right adjective. Um, you know, I might say festering, but that sounds even worse. But what I wanted to do today was try to share a video where I am going to slightly ramble about quantum gravity and my thoughts about it. This is going to be a slight ramble. I'm going to try to keep it unedited because I want this to be as natural as possible. Now, it's worth saying I've done a fair bit of travelling today, so I'm a little bit tired. So my arguments might not be as solid as ideal, but then I want to keep this channel as genuine as possible, and therefore, make videos even when I'm not at the peak of, let's say, debating capacity. I'm still definitely awake enough to discuss this. Yeah, and it's a really interesting topic. And also, it's worth saying, I did study physics. I have read a lot of physics books, but by no means am I an expert on quantum gravity. So please take everything that I say here with a pinch of salt. I am adding my voice to a sea of voices, many of which are more experienced than I am. This is more the perspective of somebody who has kind of invested a fair bit of time and has had some formal education within physics, discussing my thoughts. But take everything I say with a pinch of salt. But anyway, let's get into it. So, what is quantum gravity? Well, quantum gravity is about trying to understand how something akin to gravity, so that's usually taken to be Einstein's picture of a curved space-time, fits into the realm of quantum mechanics, because we know how to combine special relativity with quantum mechanics. Schrödinger attempted this and had, a little bit of luck. The first really successful equation combining quantum mechanics and special relativity was Dirac's equation, which ended up predicting a new type of particle called a positron, the antiparticle to the electron. And antiparticles might seem slightly wacky and out there, but we use antiparticles in medical settings. You might have heard of PET scans, and the P there stands for positron. So we use these antiparticles in a medical setting, so they're far from abstract in that sense. So a lot of good has come out of linking special relativity with quantum mechanics. It's unclear if much good will come out of linking general relativity with quantum mechanics, because we can't even agree on what we'll get when we link them together. We're still in the kind of Schrödinger phase, if you like. We're still attempting to figure out what the best route is. And I personally believe that we've been to take another physicist's words, although to apply them in a slightly different context, we've essentially taken general relativity and almost treated it like an ultimate reality, and we are trying to force quantum mechanics into it. We have become essentially trapped in a prison that Einstein built. Now, Einstein never wanted it to be a prison. When he wrote down general relativity, he was very open. This is not the end. Whereas I feel like general relativity has almost been taken as gospel. I've even seen instances where people in string theory, they're criticising quantum loop gravity on the basis that quantum loop gravity doesn't start with Einstein's field equations. It doesn't have that embedded into it. But personally, I think if we're looking for a theory more general than general relativity, so one that will integrate quantum mechanics, we wouldn't expect and we wouldn't really want Einstein's field equations to be present from the beginning. It should emerge out of the theory, but we'll need new principles to actually describe what the general ideas of the theory are. Just as when Einstein was generalizing special relativity, and therefore also describing non-uniform acceleration and things like gravity, he didn't start with Newton's law of gravity. To get special relativity, he did adapt certain Newtonian laws, but he didn't start with Newton's law of gravity when looking at a general framework of general relativity, but Newton's law of gravity came out of that later when people like Schwarzschild tried to develop exact analytical solutions for the field equations. So, Einstein's field equation should come out of whatever the correct theory of quantum gravity is, but we shouldn't restrain our imagination by insisting that the theory in its most general settings needs to be compliant with Einstein's ideas of general relativity. But that does open a massive visca. That's not the right word. A massive viscera. No, that's not. I've forgotten the word. But anyway, being willing to look at Einstein's field equations and go, well, they might just not apply, opens up so many possibilities. And it's a really deep question of what can we trust and what can we not trust. And in my opinion, and this is only my opinion, what we should be doing is we should be looking at the jump from tiny energies, where quantum mechanics seems obvious, so things like the energy levels of electrons in atoms, and seeing how that transitions to the classical realm where we're dealing with correspondingly astronomically large energies. We should look at that transition and then extrapolate that out so we can start to see what would happen when we take everyday laws of physics and extend them to situations of very high energy. Because it's when you've got very high energy where you start having huge gravitational forces, you start producing things that seem, at least according to classical general relativity, to collapse into singularities. It's there when you need a quantum theory of gravity. So I think we should be looking back to look forward. And, I think that's the road we need to go down. I think we really need to stop trying to make Einstein's field equations quantum mechanical. Or at least we need to stop trying to use that as a starting point. And kind of link with that, I feel like even when we're not, starting with Einstein's field equations, we are still remaining stuck in Einstein's prison, but in a slightly bizarre way. And it's to do with forgetting what Einstein's equations are saying or forgetting interpretations, philosophical interpretations of Einstein's equations. And it's one of the instances where I think physicists' lack of interest in philosophy, broadly speaking, and I don't mean at a personal level, I am just talking about an academic level. I know at a personal level, many physicists are interested in philosophy, but at an academic level, even when I was at uni, there was this bizarre, mildly oppressive reaction whenever philosophical questions were really brought at the fore. At least when tried to put into the cutting edge of physics. But we need philosophy because physics works with maths, but we have to interpret the maths. And when we look at Einstein's field equations, they describe space-time. And I think a problem has occurred that a lot of physicists are thinking that space-time is actually literally a thing, a physical thing. And I'm not saying it isn't, but I'm concerned that so many physicists believe space-time is actually physically present without thinking of alternate ways of interpreting Einstein's equations. Because, particularly thinking about this whilst making a YouTube series on general relativity. And the more I've thought about it, the more I've been like, it's odd to insist that space-time has to be literally physical. Because, in special relativity, space-time is an abstract geometrical structure used to explain physical observables like time dilation, length contraction, the lack of the existence of a universal now, and the relativeness of time, and all these things special relativity predicts are observable and are therefore I would argue physically real, but space-time itself is just a neat construction to do that within. I feel about space-time in much the same way I feel about imaginary numbers. Imaginary numbers are incredibly useful in calculations. Bizarrely so, but they are. But at the same time, I don't believe that imaginary quantities of apples actually exist, no matter how many times I might use imaginary numbers to describe the motion of an apple if it's swaying on a branch. I think of space-time in a similar way to imaginary numbers. We might use space-time and special relativity to create a neat, mathematical structure to make calculations in principle simpler, even if a bit more abstract. But space-time is a mathematical structure that we use because it just reduces the amount of maths, or at least steps, in our calculations. And so equally, curved space-time is equally not actually real, at least in my opinion. I think curved space-time is just as much only a mathematical tool, just as flat space-time is in special relativity. So I think when people are trying to do quantum gravity and they're starting with space-time and trying to apply quantum mechanics to space-time, that's the wrong thing to do. Because space-time isn't the actual physical thing. So trying to make it obey physical laws outside of the structure in which it was built is kind of bizarre. It's like trying to say that the complex plane has to know something about quantum mechanics. It's like, well, no. I mean, objects that we describe the motion of using the complex plane, they have to know something of quantum mechanics, because the objects exist in the physical world. But the complex plane itself doesn't have to know anything about quantum mechanics. And similarly, I don't think space-time needs to know anything about quantum mechanics, and I think that's where our venture into quantum gravity is going quite wrong, because we are attempting in a lot of situations in physics, and when I say we, I mean the physics community, and also mathematicians very deeply invested in physics. Generally speaking, quantum gravity seems to be an effort to apply quantum mechanics to curved space-time. But as I've said, I don't think curved space-time is physical. In fact, I will go so far to say that space-time was designed in the absence of quantum mechanics. So if we want to describe things like, the interior of black holes with quantum mechanics, we might have to start with a structure that is totally different from space-time. And this belief is one of the reasons why I'm very skeptical of both loop quantum gravity and also a hypergraph theory of space-time that has recently been developed. Essentially, loop quantum gravity goes, well, time and space are quantized, and I have a bit more respect for that, because time and space, I'm a bit more flexible on whether they're real or not. Or, I mean, physically real or not. But the hypergraph theory is about quantizing space-time itself. And whilst that's a beautiful idea and is allowed by special relativity, because special relativity says that all observers agree on the space-time interval, so the size of space-time, if you like, and general relativity permits that within a local frame, still, I don't think the route is to try to quantize space-time. I really don't. I mean, to give another example, if we think of kind of quantum mechanics, in quantum mechanics, we have particles where their energy states are quantized, so we can have electrons at certain energy levels. So I'll try to draw a drawing, and as those of you who have followed the channel for a while will know, I'm quite terrible at drawing, but I'll do my best. So with our atom, we've got our nucleus, and we've got kind of energy levels. Now, the rings here represent energy levels. Now, those of you who have done lots of chemistry will be telling me probably, Jamie, these energy levels shouldn't be spherical or elliptical in a lot of cases, and that's technically correct, but this gets the point across. We have energy levels that the electrons can, at least in Bohr's model, orbit in. And so when we were quantizing, we were attempting to describe the quantized energy levels. So we tried to quantize the electron's energy, a physical thing, which is the right thing to do. What we did not do is go, well, when we have the state of the electron, we actually describe the state of an electron in some Hilbert space. So this psi means the state, and this, we call this a ket, this line and this triangle-like thing. The ket emphasizes that psi is a vector in Hilbert space. But what we didn't go, to quantize the states of the electron, we have to quantize Hilbert space, because Hilbert space is a mathematical structure. It's not actually physically real. So, I feel like quantum gravity has been stuck in a very strange direction, but I understand why it's happened. Particularly because a lot of the time when one is taught general relativity, one is taught as if space-time is actually a physical thing. And because philosophy is very much encouraged in physics, that implication is never really questioned and therefore is taken almost as an unspoken axiom within physical theory. So, in my personal view, quantum gravity, a good theory of quantum gravity won't even make reference to space-time, apart from the fact of showing that in a case where, at least when we would say in terms of general relativity, space-time has weak curvature, quantum gravity does reduce to some kind of quantum field theory with special relativity built into it. But that might sound kind of down because I'm essentially going, string theory wasn't the way to go because, actually there's numerous issues with string theory. I'll have to make another video about string theory at some point, maybe title it The Downfall of String Theory. For those of you who are interested in learning about string theory and the string theory wars, which is actually a thing, thankfully, nobody literally was fighting in wars, but it emphasises how volatile the time was within fundamental physics. I would recommend checking out Sabine Hossenfelder's videos. She's a female physicist and an amazing champion of scientific communication. I hope one day to perhaps meet, even if it's virtually, Sabine Hossenfelder. She's absolutely one of my inspirations in terms of science communication. But string theory, I think it's fair to say, didn't really work out. But I'm not too surprised. And for me, one of the reasons is, string theory trusted Einstein's field equations, which a theory of quantum gravity shouldn't do. Loop quantum gravity and hypergraph theory, I don't think has got legs, because we need to stop treating space-time as a physical entity and stop trying to make it quantum mechanical. We need to look at objects that are behaving according to something like general relativity at correspondingly low energies, and then look at how those objects will behave if the energies increase and quantum mechanics becomes important. I think we need to do away with this thing of space-time. But equally, it's quite exciting. I think it's very exciting because we can break out of Einstein's prison. Now, it's worth saying Einstein, again to emphasise, Einstein did not intend to create a prison. In fact, I would argue he didn't. It's just his theories have gained so much respect that they're treated on a level of faith, which I think is slightly problematic for science. Because at the end of the day, Einstein's theories were just the best thing we had. They weren't the ultimate truth. So, I think it's really actually encouraging if space-time is not the way to go, because it implies, just like Einstein did when he was trying to unify electromagnetism and understand the full implications of Maxwell's equations, just as Einstein did with constructing space-time and doing away with Galilean relativity. So I think we will have to put general relativity respectfully to one side and come up with some new structure, a structure unlike any mathematical structure we have made before. And I think that's really exciting. So I'll end this video there. It's been a fairly impromptu video, but hopefully some interesting points, hopefully. And I look forward to doing more physics with you soon. When kind of like back home. Although hopefully, fingers crossed, in my next physics video, my dog Molly will not start barking, but we'll have to see. But anyway, been brilliant having you here. I really appreciate taking time to watch the video, and looking forward to seeing you for some wonderful physics soon. And if you've got any recommendations for what you would like to see on this channel, please do comment them down below. As so many wonderful things to cover. Always want to make content that that people would like to see. But anyway, see you soon, and stay curious.